in this section, we're going to use the important result that we did in phase 1 to prove an important theorem, which is the fundamental theorem of linear inequality. And one of these corollaries is a famous lemma that's called Farkas lemma. So we're going to prove that. And then we're going to end with the decomposition theorem for polyhedral set, where we're going to prove that any polyhedral set is the sum of a polytope and then a polyhedral cone. So let's first give some definition of cones and polyhedral sets. A set C in Rn is a cone if whenever I take vectors in the cone and two non-negative number lambda and mu, then the non-negative linear combination of these vectors belong to C. So it stays in C. In 2 dimension, for example, this will be a cone. Okay. Now the second definition is a polyhedral cone. So C is a polyhedral cone if C is defined by a matrix A, instead of all x such that A dot x less or equal to 0. So this is linear inequality, homogeneous linear inequality. Obviously, this definition verifies trivially this condition, this definition of a cone. And then the third definition is C is a finitely generated cone if C is defined this way, set of all vector B such that B is a non-negative linear combination of a finite set of vectors. So here the columns, so B is a non-negative linear combination of a finite number of the columns of A. So C is defined by a finite number of vectors. That's why it's called a finitely generated cone. And the fourth definition is a set S, set of all x such that defined by linear inequality A dot x equal to B. A is a matrix, B is a vector. This type of set is called the polyhedral set. And it doesn't, and here it's not just restricted to less or equality. So it's also, I could have a some equations that are equal and some equations that are greater or equal, or in here, because we can transform all these to equations like this, to inequalities like this. So any set that's defined by, let's call them linear constraints. So they could be less, equal, or greater or equal. That's called the polyhedral set. And finally, a set P is called the polytope if B is defined by a matrix A. So B is a non-negative linear combination of the columns of A, but the x is normalized here. The sum of the x's is 1, is normalized to 1. So this is a bounded set. And so it's a polyhedral set that's bounded, and that's called the polytope. So in the decomposition theorem, we're going to prove that any polyhedral set is the sum of a polytope and a polyhedral cone. That's what the decomposition theorem is. So let's now state the fundamental theorem of linear inequalities. And we're going to use the phase 1 of the simplex algorithm to prove it. So it states the following: either A dot x equal to B, x greater or equal to 0, either this is feasible or there exists a vector D such that D transpose B is negative and D transpose A is greater or equal to 0. So we'll call this alternative 1, and this is alternative 2. first let's note that if I multiply this by D transpose, I get D transpose A times X equal to D transpose B. So if I have this, if this is true, then I cannot have this, because if D transpose is greater or equal to 0, I multiply it by X, which is greater or equal to 0. So this whole thing is greater or equal to 0, so it cannot be negative. So the two alternatives are mutually exclusive. We can only have one of the other. Okay, so let's use the phase 1. Remember, here we have A dot X equal to BX greater or equal to 0, and here we are asking whether this is feasible or not. So we could do phase 1, which is minimize E transpose W subject to A dot X plus IW equal to B, X greater or equal to 0, and W greater or equal to 0. Remember, this is the phase 1 LP. We're gonna try to solve this problem. So, and we're gonna do the dual simplex algorithm. So I'm gonna, first of all, I'm gonna assume that A dot 1, that's the span of A dot 1, etc., A dot n is equal to Rm. Here A is an M by n matrix. All right. So I'm going to assume that the columns of A span the vector Rm. Each one of this vector is an M vector. Okay. Now I said assume without loss of generality that this is true. If it's not, let's take the case that the span is contained in Rm. It's not all Rm and different from Rm. Okay, let's assume that. Then I'm going to write Rm equal to the span, to this span, A dot 1. All right, the span of this, plus a vector where V is perpendicular to the span. All right, I can do that. I can expand for the rest of Rm with the vector space V. Okay, now here we write B. So we're going to write B is equal to B1 plus B2. So this is in V, and this is in the span. Okay, I can do that. Now, two cases. If B2 is non-zero, then we have that vector D. D will be equal to minus B2. Why? Because if I do D transpose B, that's minus B2 times B, which is equal to B2 is perpendicular to B1, so that's 0, so it's just minus B2 transpose B2, which is strictly negative. Okay, because it's B2 is non-zero, so this number is strictly negative. And D transpose A is equal to B2 times A transpose. But B2 is in V, and V is perpendicular to the span, so this is equal to 0. Okay, so here in this case we have alternative 2. Okay, I found the D satisfy the alternative 2. And then, so that's this case, and then if B2 is equal to 0, right? If this element is 0, then B is just B1, and B1 belongs to the span. So B belongs to the span, right? And therefore, by changing variables, by going to a lower dimension R, Rk, by going to this space here, this vector space span of A1 Rn, then I am just like here in this case here. I have this case, but with the lower m. So here we're going to assume this without loss of generality. We're going to assume that the column of A span Rm. So step 1, I'm going to devise an algorithm now. So step 1, I'm going to write this. I'm going to choose a basis for Rm from this vector. So I'm going to call it A dot beta 1, etc. A dot beta m, basis of Rm. Okay? And then I'm going to write this system like this. A dot beta A dot beta bar, the identity, then here 0, 0, and here is B, and then the objective, that's 0, 0, and here is just E transpose, and this -1 and 0. So I wrote this. This is exactly this. I'm just putting it with the permutation of column. I put the A dot beta here. Okay. Now we're going to use the simplex. Then we're going to transform this. Okay, by multiplying by the inverse of this matrix. So I'm going to get the identity here. Here A bar dot beta bar, right? And here goes A dot beta -1. Here is 0, 0. And this is B bar. And then the bottom stays the same. So 0, 0. And here just a bunch of 1s. Right, E transpose, and here -1 and 0. Okay. So by just multiplying by A dot beta -1. Okay. Now, so step 2. If B bar is greater or equal to 0, all right, if it happens that the right-hand side is greater or equal to 0, then if we set X star of beta equal to B bar, X star of beta bar equal to 0, right? And then here the W equal to 0, of course the W equal to 0. Then I have a system A dot X star is equal to B, and X star is greater or equal to 0, right? Same thing, simplex tableau like this. And here we have we have alternative 1. Okay. Step 3, and here we stop. Okay. Right here we just stop. So we are in alternative 1. Otherwise, we go to the step 3. There is a negative number here. All right. There are many negative numbers over here. So, and here we're going to use the dual simplex algorithm, and dual simplex with blind rule so that we don't cycle. So here then we're going to choose beta I star equal to the minimum of B bar of beta I such that B bar of I negative. Okay. So we're going to look at all the negative numbers here, the BI negative, and then we're going to look to the beta. The beta is right here. This is beta 1, etc., beta M. Okay. So I'm going to look to all the negative number. I'm just going to do the minimal index such that is negative. So I star will be our pivot row. And let's put a negative, let's say it's right here. Okay. So this is I star row, and this is, and it corresponds to beta of I star. Okay, so here we have defined the pivot row. So it's right here. So let's look now. We're doing the dual simplex. We're going to do this row divide by this row for the term that are negative. So let's look to this. This is the artificial variable. So let's just look to this. So step 4. What is the ith row here? So it's A dot okay, so this is the ith row right here. Okay. And let's assume that all these are greater or equal to 0. So I cannot pivot in these columns here. Now I'm going to show that I am in alternative 2. So in here I'm going to define D transpose to be 0, 1, 0 times A dot beta minus 1. Okay. So this is I star index. Okay. It's 0 except it's 1 on the I star index. Now, what is D transpose B? That's equal to D transpose, that's A 0, 1, 0, A dot beta minus 1, that's D transpose, times B. But that's equal to 0, 1, 0. A dot beta minus 1B, that's B bar. And this times B bar, that's just B bar I star. Right. And B bar I star, it's negative. That's our choice. So D transpose B is negative. How about D transpose A? So let's look first to D transpose times A dot beta bar. Okay. So that's equal to 0, 1, 0 times, this is beta bar, times A dot beta minus 1 times A dot beta bar. All right, by definition. But that's A bar. That's A bar of dot beta bar. All right? Well, simplex tableau, the formula from the simplex tableau. And this is equal to, remember this is the I star index. That's just A bar of I star beta bar. Okay? But here we're assuming that all this is greater or equal to 0. Okay? In step 4. So therefore we have D transpose B negative and D transpose A dot beta bar greater or equal to 0. So how about D transpose, how about the rest of the column of A? So D transpose A dot beta. All right, we did A dot beta bar. So this is equal to just 0, 1, 0 times A dot beta minus 1 times A dot beta. All right, and that's the identity. So this is equal to 0, 1, 0. And this is greater or equal to 0. All right? So therefore, here I showed that D transpose, so I showed D transpose B is negative, and I showed D transpose A is greater or equal to 0. So this is alternative 2. So alternative 2, stop. All right? So in case 1, we got alternative 1, we stopped. And in this case, when the row over here is greater or equal to 0, we stopped. That's alternative 2. Okay. So now let's do the opposite of this case now. Step 5, if A bar of I star beta bar is not greater or equal to 0. So we have some negative number in this row. Then we use the blend rule. We're going to define J star equal to the minimum of beta bar I such that A bar of I star beta bar I negative. All right? We're going to do the ratios. Okay? The minimum ratio are over here because these are zeros, and then we're going to look to the negative index among all the non-basic columns. So beta bar I represent the non-basic column, and we're going to choose the lowest index for which is negative. And then now we're just going to pivot on I star J star. So here's my I star, we define it, pivot row, and then J star. And then this is going to be our pivot element, it's negative. And we pivot in here. And then we iterate. Okay. Doing, of course, the dual simplex algorithm. So now what we have shown is we either could stop at alternative 1, or we could stop here at alternative 2, or we iterate. Okay. And since we are using the blend rule, this algorithm is not going to go forever. It's going to stop after a finite number of iteration, and this completes the proof of the fundamental theorem. Now we can say more about from this proof. We can say more about this theorem. Here, when it's infeasible, there is many D's that satisfies this set of equations. But here, if we choose this specific D, it has m-1 zeros, which means that D is perpendicular to m-1 independent column of A. So here we're going to write D is perpendicular to m-1 independent columns of A. Okay, that fact is going to be important when we do the decomposition theorem. So not only, I mean, you see here it's 0 except at I star. This is I star. Okay, we can choose the D that satisfies this set of inequalities. Okay, now as you can see here, we never use the artificial variable because they are not needed in this case. What we are really doing is the following. Basically, we are minimizing 0 transpose x subject to A dot x equal to B, x greater or equal to 0, to figure out whether this is feasible or not. And we're doing the dual simplex. So we start with A. We attach the identity matrix here. And then we have the right-hand side. Okay. And here my objective is 0 always. Okay. And then what we, in step 1, what we try to do is make the column of the identity matrix in this region here. And there we could use, for example, the Gaussian elimination. So we go to the first row. We go to the first row and find a non-zero element. Okay. And then we pivot on that element. So that will bring in the first column of the identity matrix in that column. All right. And of course, I cannot have a row of zeros because the span is Rm. Okay. And then we go to the second row and we find a non-zero element in there. And then we pivot on there, and that will bring in 0, 1, 0, etc., 0. All right. And the second row cannot have a row of zeros. Same reasoning here because the span is Rm. Okay. And so on till the end, till we put the identity matrix here, and then we end up with this tableau like this. It's an A bar. Here will go A dot beta minus 1, and this B bar. The beta will be those columns where we put those the column of the identity matrix there. Okay, so in A bar we have the identity matrix there, and then we start this process, this algorithm like that. Okay, let's now prove Farkas lemma. Let's state and prove Farkas lemma. Farkas lemma says the following: either ax equal to b, x greater or equal to 0 is equivalent to this statement here. For every d, d transpose A greater or equal to 0 implies d transpose A greater, d transpose B greater or equal to 0. That's what it says. In other words, if I take any non-negative, if I take any linear combination of the rows of A, and that linear combination is greater or equal to 0, then the same linear combination of B will be greater or equal to 0. Why? Because x is greater or equal to 0. That's simple. So we really don't need to prove this. This is equivalent to the fundamental theorem. Why? Because this statement right here is the logical opposite of this statement, right? So we have nothing to prove. It's a given. We already proved it. Now there are many forms. There are many forms of Farkas lemma. For example, let's take a system like this: ax less or equal to b. Right? Feasible is equivalent to. Let's find the Farkas lemma for this. Here, x, I didn't put x greater or equal to 0. So I'm going to write x equal to u minus v. U greater or equal to 0 and v greater or equal to 0. Any vector can be written as a difference of two non-negative vectors. That's an obvious statement. So now I apply this to here. So I have a u minus a v. And then here, less or equal, so I'll do plus iw. I introduce a new variable equal to b, and u greater or equal to 0, v greater or equal to 0, and w greater or equal to 0. Okay? So now this system is equivalent to this system here. And now this system is in this form. So this is equivalent to, for every d, and then I multiply the matrix of the system by d transpose. So I get d transpose A greater or equal to 0 minus d transpose A greater or equal to 0 and d transpose greater or equal to 0. This set implies d transpose B greater or equal to 0. Okay? So I just applied this form of Farkas lemma. So now I'm ready to state Farkas lemma for this. So for every d, now d transpose A greater or equal to 0 minus d transpose A greater to 0 means d transpose A is equal to 0. And then I have d transpose greater or equal to 0. So for every d greater or equal to 0, d transpose A equal to 0 implies d transpose B greater or equal to 0. That's Farkas lemma applies to this. Okay. And you could have any linear constraint, less or equal, equal or greater or equal. You could find the equivalent Farkas lemma for that by just remembering this. Okay, a dot x, I forgot to put feasible here. A dot x equal to bx greater than 0. Feasible means that for every d transpose A greater or equal to 0 implies d transpose B greater or equal. It's very easy to remember this statement here. So, and from here you can get any variant forms of Farkas lemma. Okay, in this section I'm going to state and prove the decomposition theorem for polyhedral sets. Before we do that, I need to state and prove a couple of facts. Facts number one: is a finitely generated cone is polyhedral. Okay, so let's prove this statement. So if I take a cone C, is a set of all B such that B is equal to A dot x, x greater or equal to 0. Right. So this is a finitely generated cone by the columns of A. I want to prove that this is equal to the set of all B such that D times B less or equal to 0 for some matrix T. So my cone is defined by some homogeneous linear inequalities. This is what we want to prove. Before I do that, let's look to the fundamental theorem of the linear inequality. So let's look to this. So there we have D is perpendicular to m minus 1 independent columns of A. right? And everything is in Rm. So D belongs to a space, so D is just lambda times some fixed U vectors, where U is a function of the matrix A, right? If you fix the, if you choose m-1 independent columns, there is only one U like that, U or minus U, either way. So and D is like that. So if I, therefore, if I normalize D, right? If I normalize D, then D becomes just, this D here is just a function of the matrix A. Okay? And now, and then the third condition is D transpose A greater or equal to 0. Okay? So these three conditions here. There are only finitely number of such Ds. Right? Because there are only so many ways of choosing m-1 independent column of A. There's a finite number of that. And then we restrict it to D transpose D equal to 1 and D transpose equal to A. Then what this becomes? This is infeasible, implies D transpose B is negative. Or another way of saying it, if this is feasible, then D transpose B, or let me say it another way. If this is feasible, that means D transpose B is greater or equal to 0. All right. And there are only a finite number of this, there are only a finite number of such a Ds. So let's call them D1, dk. Right. Finite number of Ds that's satisfied. So therefore C is the set of all B such that D1B is D1B is greater or equal to 0, etc. D transpose K greater or equal B greater or equal to 0. Right? It can't be negative because they're negative with these implies this is infeasible. So this statement is true. So this is a set of B such that D times B greater or equal to 0, where D is just the matrix. So this is transpose. So here is just D1 transpose, etc. Here D K transpose, this matrix. And this is a polyhedral cone, right? And therefore, we have we proved the that every finitely generated cone is polyhedral. Okay, I'm going to prove another fact, which is the reverse of fact 1. So, fact 2, a polyhedral cone is finitely generated. Okay, so, and let's prove that. So I'm going to take a cone C defined by some linear inequalities, a dot x less or equal to 0. So this is a polyhedral cone. I want to show that this is a finitely generated. So to make the proof easier, I'm going to illustrate it in 2 dimensions. So let me take a cone like this. And the equation of this line is A transpose X equal to 0. And the equation of this line, B transpose X equal to 0. All right? So if I draw the vector A is perpendicular to the line. That's A. and same thing with this line, that's B, right? Then this cone is just A transpose X less or equal to 0, and this is B transpose X less or equal to 0. So this cone is defined here in my case by two linear inequalities, okay, with A and B like this. Now I'm going to look to this cone here formed by this A and B. So this finitely generated cone, so this is the set of all lambda A plus mu B, lambda and mu greater or equal to 0. So this is a finitely generated cone. So in my case, I'm going to look to the set of all B such that B is equal to A transpose Y greater or equal to 0. Okay? Same thing there. So this is a finitely generated cone, just like this one. So by fact 1, this is the set of all B such that D times B less or equal to 0 for some matrix D, right? We showed that in fact every finitely generated cone is polyhedral. That means it's defined by a system of linear inequality. So this is true by fact 1. So now, so if I look to this graph here, if I draw this vector, I call it U, and this vector, I call it V, right? Then this cone right here, this cone that's finitely generated, this is this U transpose X less or equal to 0, and that's V transpose X less or equal to 0. Right? So that's my matrix D. My matrix D in this case is just U transpose and V transpose, right? And the U are over here. That's obvious in this graph. Now what I'm going to show, and then with this, now my cone, my original cone, that's just lambda U plus mu V, lambda and mu greater or equal to 0, right? And that's, therefore, I just showed that this cone that was defined by two linear inequality is finitely generated by these two vectors U and V. So we're going to do the same thing. So here I'm going to show that C is equal to the set of all X such that X is equal to D transpose Z greater or equal to 0. That's what I'm going to show. Just like in that picture there. Okay, so I'm going to show first that this set is contained in C. So let X star belong to the set of X such that X is equal to D transpose Z greater or equal to 0. Okay? And I'm going to show that X star belongs to C. To show that X star belongs to C, I have to compute A dot X star. So let's compute A dot X star. That's equal to, by doing that, that's equal to A times D transpose Z greater or equal to 0 for some Z. Okay? And I'm going to rewrite it in a different way. I'm going to write it D times A transpose times Z. Okay? Now let's go back to here. This cone is generated by the column of A transpose, right? So every column of A transpose is a ray in this cone, so it belongs to the cone. So D times A transpose is less or equal to 0. This is less or equal to 0 because that's how the cone is defined. And you multiply by Z greater or equal to 0, so the whole thing is less or equal to 0. So here I showed that AX star is less or equal to 0, and therefore X star belongs to C. Okay, so this set is contained in this set. Now we're going to now let's see, is it strictly contained in the set, or it's equal to C? So what we're going to do is I'm going to take a point in C and assume it doesn't belong here, and then arrive at the contradiction. So let X star belong to C, right? And X star does not belong to the set X, such that X is equal to D transpose Z, Z greater or equal to 0. Okay? If I arrive at the contradiction, then here, then C is indeed equal to this. So now, let's see what this means. First of all, X star belongs to C. That means A dot X star is less or equal to 0. That's the definition of C. That's first thing. And then we have X star equal to D transpose Z, Z greater or equal to 0. This is infeasible. Right? That's what it means, that X star does not belong to that. So therefore, using the fundamental theorem, it says that there exists a vector W such that W transpose X star, right, is greater than 0, and W transpose D transpose is less or equal to 0. Okay. Just reading the fundamental theorem. Okay. And here I just reverse the sign, which is it's okay. So it's just here D multiplied by D by minus D. Now this statement here, WD, so you have D times W, that's less or equal to 0 from here. So DW is less or equal to 0. That means W belongs to this set, right? So W is equal to A transpose Y greater or equal to 0 for some Y. Right? And now with that, let X belong to C. Any X belong to C. And let's see what W transpose X. All right? What is W transpose X? That's equal to, from here, that's equal to Y transpose A dot X. Okay, A transpose dot X for some Y greater or equal to 0. Now X in C, this is negative, right? A dot X is less or equal to 0. And Y greater or equal to 0, therefore the whole thing is less or equal to 0. So we showed that for every X in C, W transpose X is less or equal to 0. And this, so here we arrive at a contradiction. Right? Every X in C, W transpose X is less or equal to 0. But here we have an X star in C, and W transpose X is greater or equal to 0. So that's a contradiction. And therefore C is equal to, right? This statement is false. So therefore C is equal to this set. And this set is a finitely generated cone by the columns of D transpose. And therefore this completes the proof of that any polyhedral set is finitely generated. Ready to state and prove the decomposition theorem for polyhedral sets. So let's take a polyhedral S, which is the set of all x such that A dot x is less or equal to B. So this is a polyhedral set. And we saw earlier that this is not a specific polyhedral set. It represents all polyhedral sets. So if we have equality or greater or equal to 0, we can always convert them to this form. Okay. So this represents a general polyhedral set. Now, what I'm going to do is I'm going to construct a cone x and lambda defined by the following: A dot x minus lambda b less or equal to 0 and lambda greater or equal to 0. Okay, this cone right here. So this is a polyhedral cone. Right? Because it's defined by a set of inequalities. So therefore, by the previous fact, this is finitely generated. This is from fact 2 that we did earlier. Okay, so I'm going to call those vectors that generate this cone like x1 lambda 1, etc., till xk lambda k. Okay, from fact 4. So now these lambdas, of course, are greater or equal to 0. So some of them are going to be 0, maybe 0, but some of them are strictly positive. Let's say this lambda 1 is strictly positive. So I could assume it's 1 by just dividing by lambda, because we're dealing with a cone, right? So by normalizing this to 1, it's the same cone. So I'm going to assume that the first r are 1 until and then the other ones are zeros. Okay, so I just normalize the ones that are positive to 1. Okay, now x in S is equivalent to x1 in C, right? So if I plug in lambda equal to 1, I get exactly S, all right? And x1 in C, that means that it's equivalent to, if it's in C, then it's a non-negative linear combination of this vector. So I'm going to write it as the sum I equal 1 till r, or some mu I times x of I one, right, plus the sum of j equal r plus 1 till k, and here let's call it theta j times x of j 0, right? Where here the mu is greater or equal to 0 and the theta is greater or equal to 0, right? That's what it means that it belongs to the cone. This x1 is a non-negative linear combination of these vectors. So now So now x. So we read now x. Right? So x is equal to the sum I equal 1 till r of mu I times x of I plus the sum of j equal 1 to, j equal to r plus 1 till k of theta j x of j, right? And the mu, of course, the mu and the theta are both greater or equal to 0, right? And then 1, so I read here 1 is equal to the sum I equal 1 till r of mu I. Right? I get these two equations. So if I let P be the set of all x such that x is equal to the sum of I equal 1 till r of mu I x of I with E transpose mu equal to 1 and mu is greater or equal to 0, this set here, right? The sum of the mu I is 1. So that's E transpose mu equal to 1 and mu greater or equal to 0. So this is a polytope. Right? Because any x is a convex linear combination of some vectors, a finite set of vector xi. And then the Q, set of all x, such that x is equal to this thing here. So this is the sum of j equal to r plus 1 till k of theta j xj. And here, of course, the theta is greater or equal to 0. Right? This set here. So this is a cone. Right? Obviously, this is a cone. It's also a finitely generated cone. Right? It's generated by this xj from r plus 1 to k. And here, and this is the theorem. Any polyhedral set S is equal to a polytope plus a polyhedral cone. Right? Okay, so polytope is just the convex linear combination of a set of vectors, and the cone is also the cone generated by a finite set of vectors. So any polyhedral set can be decomposed this way. Now, so that's the general theorem. Now, if S is bounded, right? If S is bounded, it's a bounded set, then S is just a polytope, right? Because the Q is in an unbounded set, so we cannot have this. We cannot have this term, okay? So a bounded polyhedral set is a polytope. In other words, it's like this. So this is our xi, right? The polytope. It looks like this. So it's a convex linear of vectors, and these are called vertices. So a bounded polyhedral set defined by ax less or equal to b is really, so S generally is called the convex hull of these vectors, x of 1, etc., x of r. So a bounded polyhedral set is the convex R of its vertices. And vertices, when we did the simplex, is equivalent to a BFS. All right? A BFS represents a vertex geometrically. Okay. So that's the case when it's bounded. Now, a picture of a case that's not bounded. So S unbounded. For example, it's going to be like this. And let's say something like this. So this is the P, the polytope, so it's X1. This will be X1, X2, and X of 3. All right, that's the bounded piece of the polyhedral set. And then this is, and this vector here, this will be X4. This represents the, in this case, my cone is just a ray, single ray. So, so from any point in here, I could just go to infinity following that ray. So this is a the unbounded case. Okay, and this is so now we showed that bounded polyhedral set is just the convex hull of its vertices. And remember that a vertex, well, I wrote it earlier, a vertex, when you're doing the simplex, that's just a BFS. You can show that a BFS, and a vertex by definition, let me give the formal definition of a vertex. We have a set S, and V is in S, a vertex. By definition, V cannot be written then as V equal to lambda U plus 1 minus lambda V, with lambda greater or equal to 0, lambda between 1 and 0, and U and V belong to S. In other words, we cannot put V we cannot put V in a line segment. This is U, this is V, and well, I should have chosen some other W here. Right. So EW and V is here. So a vector in S is a vertex if it cannot be put in a line segment like this. Right. This is lambda U plus 1 minus lambda V. Right. That's called the vertex. And a vertex, if we're doing the simplex, a vertex is equivalent to a BFS. You could show that the basic feasible solution cannot be written as a convex linear combination of two other points in the set. So this is the end of this video. Please, if you have any comment or suggestion, please, I supplied my email address at the beginning of the video. Please feel free to send me your comment. Thank you very much.